Hi, my name is René Williams. I'm a professor at the Molecular Photonics group at the University of Amsterdam, and today I will discuss some of the photochemistry of pyrene with you. And well, there are several aspects that we will discuss that play a role. A couple of aspects that play a role in the photochemistry of pyrene are orbital symmetry effects because of the forbidden transitions. You have the formation of the dimer in the excited state, the Excimer. Pyrene also shows the so-called M effect. And the discovery of the Excimer has resulted in the discovery of the Exciplexes. For me, molecular photochemistry starts with pyrene. It is the mother of all organic chromophores and displays very special properties. Its lowest energy transition is forbidden, and as a consequence, it shows a very long singlet excited state lifetime. If the excited state of pyrene meets another molecule in the ground state, they interact and they form a complex, an excited state dimer that we call Excimer. But without that excitation, they do not interact. The Excimer only exists in the excited state. Pyrene can also act as a molecular spy. Its emission can report information about its environment, and it was the first spy. The discovery of the Excimer has resulted in the Exciplexes, an excited state complex between two different molecules like pyrene and dimethyl aniline. And these components give electron transfer in the excited state. Here we see the UV absorption spectrum of pyrene and ethanol, and we can notice that the S0 to S4 transition, as well as the S0 to S3 and the S0 to S2 transitions, are very strongly allowed. They have very high molar absorption coefficients. But the S0, the ground state to S1 transition, it is forbidden. It has a very low molar absorption coefficient. And actually, it's very easy to miss it in your measurements if you don't pay a lot of attention. Just like benzene and Buckminster fullerene, the lowest energy transition of pyrene is forbidden because of orbital symmetry effects. These forbidden transitions can become partly allowed by coupling with a vibration. So that is what we call vibronic interactions, mixing of electronic transitions with vibrational transitions. The absorption spectrum and excitation spectrum of pyrene are virtually identical, and the fluorescent spectrum also shows a very well-resolved vibrational fine structure. At low concentrations, like 10⁻⁵ molar, we again see this well-resolved fluorescent spectrum. However, if we increase the concentration, a new redshifted emission band shows up, and this is the Excimer emission. So it's the emission of the excited state dimer. And you see that it's actually a quite structureless band. So whereas the monomer emission shows very nice, well-resolved vibrational fine structure, the Excimer emission is like a broad, structureless band. We can explain this broad, structureless band by using an energy scheme, and we see that the emission actually goes towards a repulsive potential energy surface that is sloping. So that relates to the structureless emission bands. Whereas if we look at the emission of a single pyrene unit, then we have a typical scheme where we see the vibrational levels and the transitions towards these vibrational levels that give the vibrational fine structure. So this scheme is actually for, if we apply it to pyrene, the A and the D both are pyrene molecules. If we take a molecule in the excited state together with a molecule in the ground state, and they interact, they form this excited state dimer, then this electron here, or this level, it goes down. So there's a gain in energy. So this gain in energy is this here, so this is the energy of the excited state dimer. So in this way, we can use a molecular orbital scheme, a very simple one, that displays that the excited state dimer, it is lower in energy. As we said, if we look at the monomer, we have this fine structure in the absorption, but also in the emission spectrum. If these molecules, however, if they are far apart, nothing will happen. But if they come closer, then so they diffuse during the excited state lifetime towards each other, and they form an excited state dimer, a complex in the excited state. So here you see that it is lower in energy. This energy gain that is represented here is basically the same. The excited state dimer is formed and it can emit. That's actually quite special. And it emits not onto this ground state with these spaced vibrational levels, it emits onto a situation where the molecules are actually in the ground state, they repel each other. So it's a repulsive energy surface. It is sloping down, and that's why the emission spectrum is structureless. So you can measure that. And here, this is actually a time-resolved emission. So if we have a molecule, we excite it with a laser or with a pulse, then during the excited state lifetime, if it meets another pyrene molecule in the ground state, then it can form this Excimer, this excited state dimer. So you see that just after excitation, we have the typical monomer emission. However, already after 1 nanosecond, if the concentration is high enough, you can see some of these structureless bands. So this is the emission band of the Excimer. So if we now wait longer after the excitation pulse to look at the emission, then we see that the Excimer emission, it increases in time. So all the monomers are basically converted into Excimers. And at 100 nanoseconds, down here, you see that basically all the molecules that were excited, they have now formed this excited state dimer. So that makes pyrene a very special molecule. So this is actually a paper from the Journal of Chemical Education, and it sort of shows a description of the whole process that we discuss here, but it also shows this time-resolved measurements and also some kinetics. Also, actually, the kinetic equations are depicted there. But we see here that if we take the emission of the monomer as a function of time, it decays. And it decays, much faster than the band at 480. But the important thing is that as the monomer emission decays, the emission of the Excimer, it grows in. So the monomers are converted into Excimers. As the monomer emission decays, the emission of the Excimer, it grows in. So that shows the kinetics. So pyrene also shows triplet emission, a very nice resolved spectrum at around 690. So that you can depict in a typical Jablonski type diagram where you have all the separate vibrational levels. What we have discussed until now, it correlates to what you have seen before in other courses. So we can represent a molecule, let's say in one dimension, just by a simple level. And these arrows, they indicate the processes. Wavy are non-radiative and straight arrows are the radiative processes. Now, a better description is using potential energy curves. This is like a Morse potential. And you see that, especially for pyrene, this is a nice fit because it has this nicely resolved vibrational fine structure. So all these arrows, they are really peaks in your spectrum. So this is potential energy versus nuclear configuration, nuclear coordinates, and it shows the absorption spectrum. Now, perhaps even a better description is, of course, a three-dimensional potential energy surface. In reality, or the best description that we can think of probably is something like this, where you can also imagine that conformational changes actually can then make the potential energy surface diffuse in a different direction in a different way. So this is some background. So you know the emission of atoms. They can be very, very sharp lines, like for instance, the emission of lanthanides, europium, terbium. For molecules, we can have quite discrete substates. So if we have an absorption and emission spectrum that has vibrational fine structure, this indicates that situation. That's exactly what pyrene shows us. So, of course, many molecules give just quite broad absorption and emission bands, and that means that the states are not resolved. So here we see also that the medium is very important. So if we take, I think it's supposed to be azulene, the vapor spectrum has very, very nice, finely resolved spectra. If we go to hexane, well, you still see that structure, but it is blurred. The peaks are blurred together. However, in water, then you only see one band. So the medium can be very important for changing the system from quite resolved substates to more a continuum. Another aspect that you have seen before is, of course, the Stokes shift. So this is the absorption process that we discussed before. These are the absorption peaks, and you see the 0-0 transition, the 0 to 1, 0 to 2, 0 to 3. These are all the separate peaks that we can also see in the emission spectrum. So here the 0-0 energy, that is this one, is the emission. It is the peak is lower than the absorption peak. So that's called the Stokes shift. So there is some, the energy goes down if the excited state is sort of adapting to its environment. But the vibrational levels are the same, basically, or very similar. So you see that there's a nice symmetry relation between the absorption spectrum and the emission spectrum. And this is Mr. Stokes of the Stokes shift. So these are all the aspects that we see for pyrene. And in the emission, we can actually resolve the 0-0 peak, the 0-1, the 0-2, and the 0-3 peak. Now, the ratio of the 0-1 and the 0-3 peak, that is sensitive towards the medium because a polar solvent disturbs this forbidden transition in a different way as compared to a non-polar solvent. So in that way, the ratio of the I1 and the I3, it is a molecular spy. It is a polarity probe. And here you see an example and how the ratio changes with polarity. So a more polar solvent, then there's a higher ratio. So here, well, apparently 94 solvents has been tested for these effects, but here we see just a few. So for cyclohexane, a very non-polar solvent, the ratio is about half. For a very polar solvent like acetonitrile, the ratio of these two vibrational bands is almost 1.8. So pyrene is a very simple aromatic molecule, but it is influenced by its environment, well, in a very special way. So the ratio of two vibrational bands, this changes with polarity. And that, well, people use that. But basically, this is the first well, molecular reporter. That was studied a lot. But the principle that pyrene shows by the Ham effect, it can be used, well, for a lot of other molecules. And, well, some people, they focus on making special probes, molecular probes, that can sense a certain aspect in the environment. Well, and if you Google molecular probes, you get into a company. One of our former PhD students actually works there as well, but they sell molecular probes. And if you buy a vial from them, you think, hey, it's empty, but actually it contains minute quantities of a dye, and they sell it for large amounts of money. So it's an interesting business. So this represents a molecular spy or molecular reporter, molecules that can sense something in their environment. So for instance, this is D-MAN's dimethylamino nitrostilbene. So it's an electron-rich unit, like a dimethyl coupled to an electron-poor unit, like a nitrobenzene, and they're coupled by a double bond. So they're really feeling each other a lot. So the emission of these molecules, they shift from the blue to the red depending on the polarity, on the solvent. So, okay, pyrene, it is a solvent polarity probe, but the effect is minute. It is 2 vibrational bands of which the ratio changes. But the same principle is applied in this D-MAN's molecule. But then the emission, the visible emission, it changes color. So it is much more easy to, well, to observe or to probe or to use in an application. So this molecule is actually used as a probe for polymerization, because not only polarity, but also rigidity of the environment can influence the emission color or this, well, stabilization of the excited state. So it's applied in a Cure monitor, something that monitors the polymerization degree. So, as we said before, the first thing that people studied a lot was the Excimer, the excited state dimer. But at a certain point, they also discovered the Exciplex. So this is a complex that forms in the excited state and only in the excited state. So it's an excited state complex of 2 different components, pyrene and, for instance, diethylaniline. And this is a very good electron donating species, so it likes to lose an electron, but the system, the emission of the system is actually quite similar. So here you see the Exciplex emission, the Exciplex fluorescence. So it is a fluorescence from the charge separated state that comes from pyrene and dimethyl Of course, it's an electron transfer process. So the electron goes from the dimethyl to the pyrene and then back. And actually, when it goes back, it can be a radiative process. So it can emit. So this is one of the first systems that showed this effect, and it was, well, easily observed and studied quite intense. So from the Excimer came the Exciplex. And here we see very similar emission features related to the excitation of pyrene, interaction with dimethyl electron transfer interaction. And again, the Exciplex, the emission goes onto this repulsive surface. So that's why the Exciplex emission is a structureless emission band that is redshifted relative to the monomer. So we have the pyrene Excimer, we have the pyrene Exciplex with dimethyl and that led to, well, a whole bunch of new molecules that shows similar process. For instance, this is a TICT state. So it's a twisted intermolecular charge transfer state. And a molecule that shows this is dimethylamino nitrostilbene, DMABN, dimethylamino cyanobenzene. So the local emission is shown here, and the charge transfer emission, or it's not really an exciplex because the molecules, they are linked together. They are not diffusing towards each other. So the units, the diamino unit and the cyanobenzene unit, they are actually coupled. They're linked, covalently linked, but still it's a donor-acceptor system. So it is similar to an exciplex, but it's also present in the ground state. So this structureless emission from dimethylamino nitrobenzene, cyanobenzene, is a structureless emission band that is similar to the one of an exciplex. And it is called a TICT state. So that means that is the concept is that the molecules are flat in the local excited state, but in the charge transfer state, there's a twist. So there's like the dimethylamino groups, they twist relative to the cyanobenzene. So that's why it's basically decoupling as well during the process. And we have again that the energy is redshifted, the emission is redshifted in this ticked molecule. So pyrene is a very special molecule. It's a textbook chromophore. It has been studied quite intensively, but it is giving a lot of very interesting information. The aspects of the textbook chromophore pyrene that we've discussed today, they play a role in all of photochemistry. Orbital symmetry effects are always an important factor to consider. Chromophores can interact in the excited state, giving energy or electron transfer or a lot of other processes. Also, the message is the medium. The medium always influences the photophysics that is occurring in a material or in molecules in different solvents. So pyrene, it's a textbook chromophore. It's been studied a lot, but all the aspects, they play a role in all of photochemistry. Okay, thank you.